So, today we will study dielectric properties of solid. So, dielectric properties and this magnetic properties of solid. So, these are very the similarity, there is a symmetry between these two properties. So, in case of magnetic properties, that is basically response of the magnetic material in terms of magnetic field, whereas this dielectric properties, that is response of this material to the electric field. Okay. So, you will see that both are very similar. So, I will teach these properties very briefly. So, this that polarization similar to magnetization, so magnetic polarization, electric polarization, or in case of magnetic polarization, this we tell magnetization. In case of electric polarization, so we simply tell polarization. So, polarization is defined as the electric dipole moment, like magnetic dipole moment per unit volume, electric dipole moment per unit volume, right. What is electric dipole moment? So, this negative charge equal amount of negative charge and positive charge, if they are separated by distance x, then electric dipole moment, say if I write same mu. So, here mu is electric dipole moment, and this is basically q x, okay. And its direction is basically from negative charge to positive charge. So, this dipole moment, electric dipole moment direction is this, okay. So, this then similar to the magnetic property. So, another parameter here also the same susceptibility it's chi, okay. Electric susceptibility is chi is like magnetization by this magnetic field. Similarly, here polarization P, if I write this one is polarization, this polarization P equal to, if n number of dipoles per unit volume, so, and each dipole is having this moment is mu. So, then n mu will be the polarization, since n we have taken as a number of dipoles per unit volume. If I take this in general, this capital N is the number of dipoles in volume V. So, then one can write n mu by V. Okay. So, here this polarization divided by electric field. So, this epsilon E. So, here this epsilon, that is a permittivity in vacuum in air. So, we just here this comes because of this SI unit, So, earlier whatever we have seen this in case of magnetic property, they are just magnetization by E, okay, magnetization by E. So, if you in this case, that's just you can see this, if M is replaced by P by epsilon 0, then you will get this relation. Okay. So, this why this epsilon 0 has come, that so one can, as you know, this velocity of light is the square root of epsilon 0 mu 0. Okay. So, you can check it. Okay. If you know the value of the standard, this constant, you can get this value from book. If you put these two value, then it will give you velocity of light. Okay. So, c square equal to 1 by epsilon 0 mu 0. So, this in electric and magnetic, here you can see this c square is constant, right, velocity of light in air, in vacuum. So, basically mu 0, wherever mu 0, in these other cases it will be mu 0, then it is c square epsilon 0. Okay. So, this inverse relation with mu 0 and epsilon 0. So, that is the reason in SI unit this comes at the denominator. So, that the susceptibility, that is the another parameter to describe the dielectric properties of solid, and then electric field, like magnetic field, electric field that is E, okay, and magnetic field similar in case of that is magnetic field. Magnetic field H, right. So, here we have seen this magnetic induction or magnetic flux density, magnetic induction or flux density, that is B. Similarly, in this case also you have this it is called electric, in this case it is called electric displacement, electric displacement is D. Okay. So, this in analogy it is similar to B. So, electric displacement, so B, you have seen this B equal to mu H. Okay. So, mu was the this permeability, right, and then mu 0 mu r H. Similarly, here this D is basically permittivity epsilon, then E, okay, epsilon E. So, this epsilon E is epsilon 0, epsilon r, just same way this is the relative permittivity is E, right, and this equal to epsilon 0 E, that is the applied one, applied electric field epsilon 0 E plus polarization P. Okay. So, in this case you remember it was mu 0 H plus mu 0 N, right. So, here mu 0 is there, as I told this, because of this relation. So, mu 0 is there. So, now here that epsilon supposed to be epsilon, but this inverse relation. Okay. So, that is this the relation. Okay. So, this P. Okay. So, this the here from here. So, chi equal to P by epsilon 0 E, right. So, from here you can see from here that P equal to, I can get P equal to epsilon 0 E epsilon r minus 1, epsilon r minus 1, right. Same things in case of magnetic. So, chi is basically from here that P by epsilon 0 E equal to epsilon r minus 1. So, basically chi here epsilon r minus 1, right. Right. So, these are the standard parameters for dielectric properties. What is this? Polarization, susceptibility, then this permittivity. These relations are same as we have seen for the magnetic properties. Okay. So, now, so we have defined these parameters to describe the dielectric properties of solid. So, let us see the property, how properties varies with with electric field and temperature, right, as we have seen in case of magnetic property. So, here there is a basic one difference between this electric field and magnetic field, you know. So, electric field is produced by, you know, this magnetic field is produced by this solenoid, right, solenoid, long solenoid. If you take this magnetic field H or B, whatever. So, that is mu 0 N I, okay, current flowing through this. Then at the center inside this solenoid. So, this and this N is number of turns per unit length, okay. So, that is the Gibbs magnetic field. So, this is the solenoid we use in our laboratory to produce magnetic field. Similarly, to produce electric field we use condenser capacitor. So, this is called inductance. In this case this there is inductance, and in this case condenser capacitor C, capacitance C, and C, you know, this one can find out epsilon 0 A by D, this distance between these two plates. Okay. Now, if you apply voltage between these two, then there will be charge accumulation on these two plates. These are basically metal plate, these are metal plate. Okay. So, if we apply voltage V, just connect battery. So, it will be charged. So, relation how much charge will be accumulated, how much charge will be hold by these two plates. So, Q equal to C. Okay. So, Q is proportional to V voltage, whatever voltage you will apply. So, amount of charge will be. So, in this case charge, whatever the function of charge. So, other case is a function of I, you know. Okay. So, So, this V is basically C electric field by not by into D, right, into D. So, electric field one can write in Q by C D, right, Q by C D, that is the capacitor, Q by C D. And Q by C D, if you replace C Q charge by epsilon 0, so d d will go. So, basically epsilon 0 A, right. So, here is very important, you see this charge on this plate, right. So, this and this area of this plate, okay. So, this I can write charge density, surface density, charge surface density on this plate, that is sigma by epsilon 0. So, electric field is basically the charge density on the plate on the surface by this epsilon 0. Okay. So, this is very important relation, and later on I can show you in principle what I wrote E epsilon 0 E that chi we have chi equal to we wrote P by epsilon 0 E, right, epsilon 0 E, right. So, if I electric field yes. So, here what I want to show, that want to tell you that basically the surface charge density and this polarization they are probably here I can show directly E equal to this, again E equal to yes, I think epsilon 0 E, or I can write from here I can write E equal to P by epsilon 0 chi, okay. Chi is susceptibility, and so from these two form, and chi is nothing but what was that, epsilon chi was epsilon r minus 1 kind of things, right. So, this P from here you can see E equal to this sigma by this epsilon 0. Now, in case of ears, is it I just what I wrote this epsilon r equal to chi equal to epsilon my r minus 1, that is true. In case of ear chi is 0, that is true. So, this is the basically related with the permittivity, okay, as in this case is this. Okay. So, in case of so here this P and this surface charge, they are related, and generally we tell that this P is equal to is surface is equal to the surface charge density on the surface. Okay. So, electric field is related with the surface charge density, and this polarization also it is related with the surface charge density. So, in terms of either in terms of surface charge density or in terms of Q, as P I have shown you, that the dipole moment per unit volume. So, dipole moment is nothing but the charge into the separation of them, charge into the separation of them, charge into the separation of them. Okay. So, so that is thus this electric field and polarization is related with the charge, and again here just I try to tell you that they are related with the surface charge density, whether in terms of surface charge density or in terms of charge we can express them. Okay. So, here just what I want to show you that if I take two capacitor plate, okay, it will produce electric field, and this field direction is, you see, it is the this direction, electric field direction. If I write this is say E0. Okay. So, inside there is the dielectric material. So, then electric field generated by these two metal capacitor plate is this E0. Now, if I put dielectric inside this say one slab of dielectric material, inside this capacitor plate. So, these are dielectric material, okay. So, then what happens? Then immediately, if it is dielectric material, immediately there is a on the surface of the dielectric. So, there is a induced charge, You can think that there will be induced charge. Okay. There will be induced charge. So, what happens? This effective charge will decrease there, whatever the charge here. So, that charge, amount of charge, effective charge will reduce or will decrease, right. So, this, so as if here now you see this negative charge and positive charge. So, this basically this because of the polarization of this metal, when it is put in this electric field, they will be polarized, there will be induced polarization, and that because of that polarization. So, this and this positive charge. So, this polarized atoms or molecules or dipoles. So, their negative side, it will be attracted this side, positive side will be attracted this side. So, thus it is we tell this this positive one is induced negative charge on the surface of the dielectric, and this negative charge induced positive charge on this surface of the dielectric, okay, without considering any from any atomic view of point. So, just we can see this one, and then here you can see this electric field for this charge, okay. So, this direction will be this direction, right, and this say if we write E1, okay, this one due to the polarization. So, polarization of this dielectric material. So, this E1 is this one. So, here effective electric field, whatever this material will see, okay, or we tell macroscopic, not microscopic, macroscopic electric field, that is we generally consider the external electric field whenever we apply external electric field without any dielectric in vacuum, that is E 0. When materials, when dielectric materials are there and we apply this electric field. So, these materials will see the electric field, that is E equal to basically E 0 minus E 1, E 0 minus E 1, right, yes, E 0 minus E 1. And so, this E is called basically microscopic, not microscopic, macroscopic electric field, okay. So that's, so generally we write this E that as a external applied electric field when it is in vacuum. So, this E 1 is 0, okay. When it is in on a some material, dielectric material, then this E 0, that is reduced by this one, okay. So, electric field in material is less than the electric field in vacuum. So, this is just the difference. In case of magnetic field it was different, okay. In that case, this in magnetic material, this magnetic field is enhanced, okay, is enhanced, but here it is decreased. But here, so their magnetic field is increased, that we express in terms of B, okay. So, this one we are not expressing in terms of just D, but this we have taken, this is the resultant one we have taken as a electric field E, okay. So, now D is defined. So, as if this material will see this electric field, it will take that, okay, externally this electric field is applied. Now, that we have taken as a electric field, external electric field, which is similar to still it is similar to H. So, B compared to B, so that is D is defined as now this electric field E we have defined as a epsilon E, right. So, this E is this E, not E 0, okay. In vacuum it will be E 0 because this will be 0, this effect will not be there, okay. So, this is electric field, it is not electric displacement. Electric displacement similar to this is defined now, this D is similar to B. So, this we defined H, okay. So, macroscopic electric field is basically this E, not E 0, metal will see this electric field. So, that is equivalent to the whatever the way we define this magnetic field, okay. So, that is important difference between these two. And then now then what we would like to see. So, that is macroscopic electric field. As a whole, this material will feel this electric field E. Now, what is the field? What is the field atom will see? So, in point of microscopic point of view, from microscopic point of view, what say at here one atom is there, when this field E is applied. So, this material will see this field E. So, whether this atom at the center here or anywhere, whether it will see the same electric field or that field will be different. So, that field will be different, it will not see this field, it will see field that is called local electric field, local electric field, okay, local electric field which atom or molecules in the material sees. Okay. So, that is if I write E local, locally what is the field that atom will see. So, that is different from this field. Okay. So, that has that contribution will come in this field. So, one is E 0 from this whatever field that it will see, then whatever field from this surface charge of the dielectric. So, that it will see. Okay. Then what it will see? It will see this whatever the polarization or dipole moments are surrounding, either it is induced dipole moment or permanent dipole moment, whatever. So, because of this it will feel some it will see some field. Okay. So, that Lorentz basically calculated this local electric field. So, he find out the process how to calculate. So, what he has done, so here it is taken a sphere, it is taken a sphere, radius of sphere is greater than the dimension of the dipole, Okay. So, now it is, so Lorentz calculated this one, that he told that here, so because of these dipoles surrounding this whole dipoles, okay, so there will be effect on this, it will give electric field on this. Okay. So, if you just make a cavity inside this dielectric material, right. So, make a cavity inside the array. So, take out this dielectric material from here. Okay. So, at the center of this, at the center of this sphere, this one atom, it will see the electric field because of the surface charge on this sphere, surface charge on this sphere. So, surface charge on this sphere, because it is already polarized due to this external electric field. So, it will be polarized like this. Okay. And this other side negative, other side negative. Okay. No, because polarization is in this direction. So, I think this I have to put here. So, polarization, direction of polarization is basically negative to positive. So, here, so direction of polarization for this electric field is this direction, but positively that is the polarization direction, that is the polarization direction. So, here polarized in same way. So, this will be negative, this will be negative, this will be negative, and this will be positive. Okay. This will be positive. Okay. So, this will see the dipole moment or polarization, or that is equivalent to the surface density, charge density on this surface. Okay. So, this, so it will produce electric field at the center, that if it is, that is E3, sorry E2, that E2 is the electric field produced by this surface cavity, by this surface of the sphere. inside surface of the sphere. That is so now this material we have taken out, but metal is there in principle. So now I have this surrounding this. So this material is there. So dipole moments are there. Okay. If it is polar material, means if it has the permanent dipole moment, okay. So due to that dipole moment, so it will see the also this will contribute the electric field at the center. So metal inside this cavity whatever was there, so because of that it will fill electric field, okay, center. So that if it is E3. Okay. So this local electric field will have this 4 contribution. So this E0 is this one, that is the standard one. This basically is surface density on this. I can write E0 on this external plate, and that is by epsilon 0 electric field epsilon 0, right. And this one E1 is basically surface density on this. If I write it is due to polarization sigma p surface density. So this will be epsilon 0, okay, and this negative sign, okay. And now E2 we have to calculate. So E2 we have to calculate, and then E3. If you see this E3, if it is non-polar material, so E3 is 0, because this here because of dipole moment inside this permanent dipole moment only it will see the electric field. So this E3 will be 0, or in case of dipole moment also, if depending on the structure of this material, okay, depending on the structure of this material, so this field can be 0 also. So one can show this calculation, but I will not go into details. So here it will see this electric field 0 because of this, if it is non-polar dielectric. Even if it is polar dielectric, if cubic symmetry is there, this metal have cubic symmetry, okay, then also one can show this E3 will be 0, okay. So if it is not cubic symmetry, others, so in general E3 may not be 0, but non-dipolar case, non-polar case, or in case of polar, but there is a symmetry, let us say the cubic symmetry. So E3 is 0. So let us do for the either considering the cubic symmetry for polar case or the non-polar magnetic material. So E3 is 0, E3 is 0. So E3 is basically 0. Okay. So this, so then local field here it will be this. So this we write generally this is E macroscopic electric field, okay, and then your local field. Okay. So E is there, whatever just we use this electric field as a field which this as a whole this material C, and then additional field atom will see, that is E2 in case of polar material, non-polar material, or cubic symmetry of polar material, okay, cubic symmetry of polar material. So so now our task is to calculate this E2, and this called E2 is called the Lorentz field. E2 is called the Lorentz field. It's called the Lorentz field. Okay. So now I have to calculate only this one. Okay. So then I think I will calculate in next class. So let me stop here. Thank you.